Now that we have seen properties of Stirling numbers of the second kind, let us look at Stirling numbers of the first kind. Stirling numbers of the first kind. Okay, so write the sequence xk or xn n is equal to 0 to infinity in terms of xn. N is equal to 0 to infinity. Example, x3 in terms of xn, n is equal to 0 to infinity, gives me, well, x3 is equal to x times x minus 1 times x minus 2, which is equal to x cubed minus 3x squared plus 2x, which is equal to 0 times x to the 0 plus 2 times x to the 1 plus minus 3 times x squared plus 1 times x cubed. Right? More generally, we can again write these out. Okay, and these are given by what we will call small xn. More generally, small xn is equal to summation k is equal to 0 to n negative 1 to the n minus k small s of n comma k x to the k. You'll see why we have these negative 1 to the n minus k when I draw the figure. Observe, and I'll draw the figure. So with Sn comma 0 is equal to 1 if n is equal to 0, 0 if n greater than or equal to 1, similar to the previous case. So let me actually do these in cursive. Small s, Sn comma 1 is equal to n minus 1 factorial, and Sn comma n is equal to 1. N is equal to 1, 2, 3, dot, 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 n is equal to 0, 1, 2, dot, dot, dot. Okay, and similar to Stirling numbers of the second kind, we can write them in something similar to a Pascal's triangle. Okay, here the triangle looks like 0, 1. It again goes to 0, 1. These are 1, 1, 1, 1. So I get 0, 1, 1. And now here's where things start looking different. Okay, now I get 2, 1, 2, 1, 2, 1. All the right edges are again going to stay 1, but the left edges get the value equal to the row number. So for the first one, the left edge was 0. Second, it was 1 everywhere. Third, it is 2 everywhere. Well, for the 0 it is 0. For the first one, it is first 1. For second, it is 2. So I get 0. 1 times 0 plus 2 times 1 is 2. 1 times 1 plus 2 times 1 is 3. 1 times 1 is 1. Oops. I get 3, 1, 3, 1, 3, 1, 3, 1. So this combination is really easy to remember. So I get 0, 3 times 2 is 6, 2 times 2 plus 9 is 11, 3 plus 3 is 6, 1 more, let's do it just for the sake. 4 1 4 1 4 1 4 1 4 1, and I get 0 24 50 35 10 1, and so on. Okay, so this is the pattern that is generated for Stirling numbers of the first kind. Okay, once again, for notational convenience, let snk, small s and k is equal to 0 if k is smaller than 0 or k greater than n. Okay, maybe I should have labeled these above. I'll quickly label them. So exactly similar to before, this is a small s 0 0, small s 0 1, small s that should be 1 1, one 0 1 1, small s 2 0, small s 2 1, small s 2 2, and so on. Right? You have seen the exact more or less picture drawn same way for Stirling numbers of the second kind. Then theorem: these numbers satisfy for 0 smaller than or equal to k smaller than or equal to n, small s of n comma k is equal to small s of n minus 1 comma k minus 1 plus n minus 1 times small s of n minus 1 times k, small s of n minus 1 comma k, and proof is assume n greater than or equal to 1, otherwise it's trivial. Assume n greater than or equal to 1. Once again, if you do it for 0, Sn minus 1 is 0, n minus 1 is negative 1, Sn minus 1 is 0. Those do not make sense. So you get that it is all equal to 0. Well, you don't get anything substantial. So recall, similar to what we did for Stirling numbers of the second kind, summation k is equal to 0 to n, negative 1 to the n minus k, small s of n comma k, x to the k. So x to the k and k minus sorry these should be n minus 1 n minus 1, whoops, that should be n and this should be n minus 1 is equal to summation k is equal to 0 to n minus 1, negative 1 to the n minus 1 minus k, small s of n minus 1 comma k, x to the k. Now, therefore, xn is equal to xn minus 1 times x minus n plus 1. Right? If you expand these out, this product is up to xn minus 1 plus xn plus 2. This goes to xn sorry, x minus n plus 2, and this one is up to x minus n plus 1. So the only term missing is x minus n plus 1. Multiplying, I get this is equal to summation k is equal to 0 to n minus 1 to the n minus 1 minus k, small s of n minus 1 comma k, x to the k, x minus n plus 1. Exactly similar to the stuff we did before. I will split this up into two cases. Summation k is equal to 0 to n minus 1. Negative 1 to the n minus 1 minus k, small s of n minus 1 k, x to the k plus 1 minus n minus 1 times summation k is equal to 0 to n minus 1, negative 1 to the n minus 1 minus k, small s of n minus 1 comma k, x to the k. Okay, great. And now, combining like terms as we did before, we get this is equal to summation k is equal to 0 to n, negative 1 to the n minus k, negative 1 to the n minus k, s of n minus 1 comma k minus 1 plus n minus 1 s of n minus 1 k, x to the k, right? And therefore, comparing it to the previous one, I get small s of n comma k is equal to small s of n minus 1 comma k minus 1 plus n minus 1 times s n minus 1 comma k. 0 smaller than or equal to k, smaller than or equal to n. That's my recurrence relation. I can use that to get a closed form. What we want to show small s of n comma k is equal to number of arrangements of n distinguishable objects into k non-empty circular permutations. So basically, I am going to divide it into k circular permutations, right? Proof? Induction on k. Proof. Induction on k. Induction on n, not k. Well, let us look at n is equal to 0. N is equal to 0. Snk, we know that is equal to 0, is equal to 1, and the number of such arrangements is also equal to 1. There's only one way. You put nothing in everything, right? So for n greater than or equal to 1, define S is equal to set of all arrangements of 1 to n into k non-empty circular permutations, and then want to show that absolute value of S is equal to S n comma k, right? So define S prime is equal to set of elements in S for which the circular permutations containing n has length 1 and let S prime prime is equal to complement of S prime in S. Okay, since they are complements, I get that therefore cardinality of S is equal to cardinality of S prime plus cardinality of S double prime by my addition principle, right? Well, what is the size of S prime? Well, S prime is, I am arranging my circular permutations and there is one circular permutation that has length exactly 1. So basically the element n is kept separately, right? So it is exactly equal to number of arrangements of 1 to n minus 1 into k minus 1 circular non-empty circular arrangements, non-empty circular permutations, right? Since I'm just keeping n separately by its own, which is exactly as n minus 1 k minus 1. Now we have to look at how S double prime is constructed. Find S double prime cardinality, right? So what we do is construct it in 3 stages, or construct it in stages. Construct it in stages. Okay. Stage to do number of choices. Well, in the first stage, pick an arrangement of 1 to n minus 1. Pick an arrangement of 1 to ... n minus 1, which you're dividing into k non-empty circular perms. Into k non-empty circular permutations. Okay, so you have basically n minus 1 dots that you're putting in some circles. Well, the dots are labeled, but for the sake of drawing, I'm not labeling them. But whatever, something like this. 1, 2, 3, 4, 5, 6, maybe. Something like that. How many do I have? S n minus 1, k, by definition. And in stage 2, insert n in one of them. Insert n. Well, how many choices do I have of inserting n? I have exactly n minus 1 choices. Because, think about it. I am basically inserting n in one of these somewhere, right? I can say that, I am inserting n to the left of one of these numbers, or to the right of one of these numbers, right? So I can either insert n to the right of 1, or insert n to the right of 2, or insert n to the right of 3, blah, 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 blah. I can insert it somewhere. Well, therefore, S double prime is equal to n minus 1. Since there are n minus 1 ways of inserting S, into the total number of total number of circular permutations, ways of writing in circular permutations that there was, which was Sn minus 1k. And therefore, my entire group S is equal to S prime plus S double prime, which is equal to S n minus 1 k minus 1 plus n minus 1 S n minus 1 comma k, which by definition is S n comma k. Okay, and that ends section 8.2. This is all there is in this section. This is the Stirling numbers of the fist.